Stars are an optical illusion. I know how that sounds like I'm saying the night sky is fake or that astronomy is some kind of misunderstanding. That's not what I mean. Stars are real. They fuse hydrogen. They sculpt galaxies. They forge the elements in our blood. But the thing you experience as a star, a bright dot sitting calmly in a vast three-dimensional space, is not the star itself. It's a reconstruction, a compressed message, a picture assembled from whatever information is allowed to reach you. And if we follow that thought all the way down, it doesn't just change how we think about starlight. In a few minutes, it drags us straight into black holes, the physics of information, and a radical idea that the deepest description of reality may live on boundaries, not in volumes. So, here's the promise. By the end, we'll come back to the night sky and ask a deceptively simple question when you point at a star and say, "It's there." What does there actually mean? To get there, we need to be careful with one word: illusion. In everyday life, an illusion is a mistake. A mirage that vanishes when you walk closer. A trick that collapses when you learn how it's done. But in physics, something can be illusory in a different way. It can be real and reliable, yet not fundamental. It can be an effective picture that works perfectly at human scales, while hiding a deeper, more microscopic story underneath. Think about color. Color is real. It shapes your entire experience. But color isn't a substance floating in the air. It's your brain's interpretation of certain frequencies of light interacting with your eyes. The redness isn't a little red paint on the photon. It's a translation. Or think about temperature. Temperature is real enough to burn you, but it's not a basic ingredient like electron or quark. Temperature emerges from countless microscopic motions. Zoom in far enough and you stop seeing hot and cold. You see particles colliding, exchanging energy, spreading out statistically. Temperature survives as a summary, not as a tiny object you can point to. That's the kind of illusion we're talking about. Stars aren't imaginary. The illusion is the way your mind and even your instruments turn a thin stream of arriving information into the feeling of a stable object sitting in a place. Because when you look at a star, you are not reaching out and touching it. You're intercepting a trickle of photons, quanta of the electromagnetic field. Tiny events that were emitted long ago traveled across an expanding universe, threaded through dust, magnetic fields, and gravity, and then ended their journey in your eye or your telescope. You're not holding the star, and that seems obvious until you ask something uncomfortable. If everything you will ever know about distant reality arrives only as information on a boundary on a sensor, on a screen, on your retina, then how much of the three-dimensional world out there is something you directly know, and how much is something you infer? Hold that question. It's going to matter more than it should. Let's build intuition with a simple modern analogy. Imagine you're watching a live sports game on your phone. It feels immediate. You react as if you're seeing the event itself. But you're not seeing the event. You're seeing an encoded stream, compressed, packaged, delayed, corrected for errors, reconstructed by hardware, processed by software, and finally displayed as pixels. The game is real. The players are real. The physics of a ball in flight is real. But what you experience is a carefully engineered representation. It's faithful within limits. It's useful. It's not a lie. And yet it's absolutely not the same thing as being in the stadium. Now look up at the night sky. The sky gives you something like a live stream from the universe. But it's a stream with extreme constraints. The bandwidth is low. The delay is huge. And crucially, you never receive the star. You receive only what can propagate to you, light, and occasionally other messengers like neutrinos or gravitational waves. Even the idea of live breaks down immediately because the universe doesn't provide a universal present. When you look around your room, you're seeing the past too, but the delay is so tiny you can ignore it. Light takes about a nanosecond to travel a foot. Your brain can treat the world as now. But the night sky is different. Some stars you see are minutes in the past, some are years, some are thousands. If you look beyond the Milky Way, you can see galaxies millions or billions of years in the past. The sky is not a snapshot. It's a collage of different ages stitched together into a single view. So the first layer of the illusion is time. There is no single right now spread across the cosmos. Yet your mind insists on painting the sky as a unified present. And there's a second layer, even stranger, location. We like to imagine that each star is a dot on the inside of a giant sphere. We point to it. We say it's there. But even in classical physics, there is already a subtle statement because gravity bends light. A star's apparent position can be shifted by the curvature of spacetime. Whole galaxies can act like lenses. Sometimes the same distant object appears in multiple places in the sky, multiple images of one source because the universe routes light along different paths. In those moments, you see the illusion openly. Location is not something you read directly off reality. It's something you infer from signals that have traveled through a curved geometry. And now we can take the next step from classical intuition to quantum intuition. Classically, it's tempting to picture light as tiny particles flying along definite paths. The star throws them out. They travel. You catch them. Simple. Quantum physics doesn't let us keep that picture intact. It replaces it with something that sounds abstract, but is actually more honest. A photon is not just a pellet with a location tag. It's an excitation, an event in the electromagnetic field. Between emission and detection, the most accurate description is not, the photon is here. It's, if we detect it here, we get this probability. And that changes what we mean by seeing. Because seeing a star is not receiving a miniature piece of the star. It's performing a measurement. Your detector clicks. Your retina absorbs energy. Information becomes available at your boundary. The star, as an object with a shape and an interior and a position, is a model you build to explain patterns in those clicks. That model is extraordinarily good. It lets you do astrophysics. It lets you predict stellar evolution. It lets you measure chemical composition by splitting starlight into spectra. It lets you infer temperatures, magnetic fields, and motion. But it's still a reconstruction built from boundary data. And at this point, you might think, okay, this is just epistemology. Of course, we learn about faraway things through signals. What else could it be? Here's what else. There are places in the universe where boundary data stops being merely a practical limitation and starts behaving like a fundamental rule. Those places are black holes. Black holes are where gravity becomes ruthless about information. Drop something toward a black hole, and from far away you see it approach the event horizon, the point of no return. But you never see it cross. Its light gets stretched to longer and longer wavelengths. It redshifts, it dims. It slows, as if time itself is thickening near the horizon. Eventually, the signal fades into darkness. From the outside, it looks like the information is trapped. And then Stephen Hawking added the twist. Black holes are not perfectly black. They radiate. Quantum effects near the horizon produce what we call Hawking radiation. Very slowly, over unimaginable timescales for astrophysical black holes, a black hole can lose mass and evaporate. If a black hole can evaporate away, and if nothing escapes from inside, then what happens to the information about what fell in? Not just a list of properties like mass and charge, the detailed quantum state, the full message that tells the difference between one arrangement of matter and another. If that information is destroyed, it would violate a deep principle of quantum mechanics, that evolution preserves information, even when it scrambles it beyond practical recovery. But if information is preserved, it has to go somewhere. It has to be encoded somehow. It has to be able to reappear in the outgoing radiation, at least in principle. So where could it be stored? Your everyday intuition says inside the volume of the black hole, somewhere in the interior, behind the horizon. But black holes don't behave like that. There is a remarkable result in physics. Developed through the work of Jacob Bekenstein and Stephen Hawking, black holes have entropy. And that entropy scales not with volume, but with area. Let that land. In ordinary matter, more volume means more room for microstates, more ways to arrange the internal degrees of freedom. Entropy scales with how much stuff can fit inside. But for a black hole, entropy scales with the area of the event horizon, the surface, not the interior volume. That is a crack in our intuition. And through that crack, something enormous starts to show. If the maximum information content of a region is proportional to its boundary area, then maybe the fundamental storage of reality is not volumetric. Maybe nature is telling us that the deepest bookkeeping happens on surfaces. This idea became known as the holographic principle, developed and championed by physicists, including Leonard Susskind and others, as they wrestled with the black hole information problem. The holographic principle, stated carefully, is not the claim that the universe is a fake projection. It's a claim about equivalence, that a gravitational world in some region can be fully described by degrees of freedom living on the boundary of that region in one fewer dimension. Like a hologram in a museum, a thin plate that somehow stores enough information to reconstruct a three-dimensional image. The image is not fake. You can walk around it. It has depth. It responds to perspective. It behaves like a three-dimensional object. But the information that makes it possible lies on a surface. Now return to the night sky. You never access a star's interior directly. You infer it. What you actually receive is radiation that reaches your boundary. In that sense, astronomy is already holographic. You reconstruct a three-dimensional universe from a two-dimensional sky. But holography in modern theoretical physics goes further. It suggests that in some cases, the boundary description isn't just a convenient reconstruction. It can be complete. And that raises the question we opened earlier. Is this boundary idea just a metaphor, a poetic way of speaking? Or do we have any situation in physics where it becomes exact, like a theorem? This is where ADS-TF enters. ADS-TF is one of the most striking proof of concepts in theoretical physics. It proposes an exact equivalence between two very different descriptions. On one side, a theory with gravity living in a certain kind of space-time called anti-de Sitter space, or ADS. On the other side, a quantum field theory living on the boundary of that space-time, no gravity, often described as a conformal field theory, or CFT, two different languages, one underlying reality. In this duality, a higher dimensional gravitational world can be encoded in a lower dimensional non-gravitational theory. Geometry in the bulk corresponds to quantum information structures on the boundary. Questions that are hard in one description can become easier in the other. Now we have to be honest about limits, because this is where people often leak too far. Our universe, as far as we can tell, is not exactly anti-de Sitter. Cosmologically, we observe something closer to accelerated expansion, more like de Sitter behavior on large scales. The clean mathematical setting of ADS-TF doesn't map directly onto our cosmos in a simple way. So it would be wrong to say ADS-TF proves the universe is literally a hologram in the pop science sense, but it would also be wrong to shrug it off. ADS-TF shows that holography can be real, exact, not a metaphor, not an analogy, a genuine equivalence between a world with gravity and a world without gravity, between a bulk and a boundary. And once you've seen one example where space-time geometry can emerge from a deeper, lower dimensional description, you can't unsee the possibility, because it suggests a new way to think about space. Maybe space is not the stage that holds everything else. Maybe space is part of the story that emerges when information organizes itself in the right way. If that feels too abstract, bring it back to emergence, something we know is real. A traffic jam is emergent. There's no single molecule labeled jam. It's a collective behavior that appears when many independent drivers interact under constraints. The jam can move backward like a wave, even though every car is trying to move forward. The jam is real, measurable, and causally powerful, yet it exists only as a pattern in many parts. Sound is emergent. A single molecule doesn't carry music, but large-scale coordinated motion does. Now imagine space-time as something like that, a stable, large-scale pattern that arises from microscopic degrees of freedom we don't yet fully understand. In some modern research directions, entanglement, the quantum linkage between degrees of freedom, plays a central role in how geometry could emerge. The idea, stated cautiously, is that the connectivity of space might reflect the connectivity of quantum information. That doesn't mean everything is just thoughts or anything mystical. It means that the relationships that quantum systems have with each other, their correlations, could be the raw material from which the feeling of continuous space is built. What is established here and what is speculative? It's established that black holes have entropy proportional to horizon area. It's established that Hawking radiation exists as a prediction of quantum field theory in curved spacetime. It's established that ADS-CF is a mathematically precise duality in its proper setting. It is actively researched and not settled in a final way how to extend these ideas cleanly to our cosmological universe, and what the fundamental degrees of freedom of spacetime are in the real world. And it is speculative to claim we already know the final answer, that our universe is literally encoded on some cosmic boundary in the same neat way as ADS-TF. So we should keep our humility. But even with that humility, a clear message remains. The universe has strong hints that information and boundaries matter more than our classical intuition expects. Now we can return to the title claim stars as an optical illusion and sharpen it into something precise. When you look up, what you experience is a star rendered as light on your boundary. You can't step outside that boundary. Even if you fly toward the star, you don't escape the rule, you just change which photons you intercept, from which angles, at which energies, with which delays. You keep building the star from signals. And if holographic ideas are even partly right, then this isn't just a limitation of human biology or current technology. It may be the architecture of physical description itself. The star, as a three-dimensional object out there, is real at the level of effective physics. It is as real as temperature and waves and storms and traffic jams. It has causal power. It burns. It explodes. It seeds space with heavier elements. But at a deeper level, the star may be less like a thing and more like a stable pattern in information, an emergent object in an emergent spacetime, inferred from a boundary-limited stream. Imagine an idealized scientific instrument, a perfectly sensitive spherical shell of detectors surrounding Earth. Not a telescope pointing in one direction, an all-sky boundary that records every photon at every wavelength that hits it. It records arrival times with absurd precision. It records polarization. It records phase information when possible. It measures everything you can measure about incoming radiation. Now ask, in principle, could you reconstruct the universe outside the shell from the information that derives on the shell? In practice, we'd be limited by noise, by quantum uncertainty, by the fact that not everything reaches us, by the fact that the universe is dynamic. But the point of the thought experiment is deeper. It asks whether the outside world is something over and above the totality of information that can ever reach a boundary. Everyday intuition screams, yes, of course, there's more. There's the whole star, the whole galaxy, the whole three-dimensional expanse. But black holes have taught physicists to be suspicious of that scream, because black holes suggest that what seems like inside may not increase the fundamental information content beyond what can be written on the boundary. And if that can happen for a black hole, the most extreme object we know, then it becomes reasonable to wonder whether our sense of volume and interior is an emergent convenience, not the foundation. Now we can close a loop. We opened at the very beginning. What does there mean when you point at a star? At the human level, there is a direction in the sky. It's a location you can triangulate. It's an object you could, in principle, travel to. What is a perfectly valid description? At a deeper level, there might mean a consistent cause of the information arriving at your boundary, a stable, explanatory structure in your best physical model, a feature of a reconstructed spacetime that itself may be derived from more fundamental degrees of freedom. And that's why illusion is the right word if we use it carefully. The star you see is like a perfectly rendered icon on the screen. The icon corresponds to something real. The correspondence is stable. You can do science with it. You can navigate by it. But the icon is not the underlying code. Now, before we end, let's bring this down from the abstract to the concrete with a few implications ways this perspective changes how the night sky feels. First, the sky is not a window onto a single moment. It's a time-layered interface. Every star is a different timestamp. When you look at Orion, you're looking at a quilt of different delays. If a star in that pattern died yesterday, you might not know for hundreds of years. The present you feel when you look up is something your mind manufactures. Second, position is partly inference. Because light is bent, delayed, and sometimes split, what you see is not a simple geometric truth. Even without exotic holography, general relativity already teaches that the universe is not a rigid stage. Spacetime itself participates in what can be seen. Sometimes the cosmos shows you multiple images of the same object and dares you to admit that where it is not always a single clean answer. Third, near horizons, the boundary first view becomes unavoidable. As a star collapses toward forming a black hole, the outside observer and the infalling observer can give very different accounts of what happens, and yet physics can reconcile them. In these extreme regimes, what information is available to which observer stops being a philosophical add-on? It becomes part of the mechanism. So when we say stars are an optical illusion, we're not making a cynical point about perception. We're pointing toward a deep theme in modern physics that what you call reality is tightly linked to what can be encoded, transmitted, and recovered as information. Now, let's recap slowly. Stars are real astrophysical objects. Nothing in this story denies that. But your experience of a star is boundary limited. It's built from photons that arrive late, filtered by the universe, interpreted by detectors, and assembled into a model. Quantum physics nudges us away from thinking of light as tiny labeled pellets and toward thinking in terms of correlations and measurement events. Black holes force a crisis. If information is not destroyed, it must be accounted for. And black hole entropy scaling with area, not volume, suggests that the ultimate accounting may live on boundaries. The holographic principle proposes that a lower dimensional boundary description can encode a higher dimensional gravitational world. CFD provides a real exact proof of concept in certain kinds of universes, even if our universe is not exactly that kind. And emergence ties it all together. Space, time, and objects can be real and causally powerful, while still not being fundamental in the deepest description. So yes, when you look at a star, you are looking at something real, but you are not looking at the star in the naive way your brain wants to imagine. A tiny lamp sitting directly in a three-dimensional container called space, presented to you as it is right now. You are looking at a message, a boundary event, a reconstruction. And if that makes the universe feel less real, flip it around. What kind of universe is so consistent that it can compress itself into light, survive vast distances and deep time, be encoded on boundaries, and still let conscious creatures reconstruct a cosmos full of structure? Maybe the night sky isn't less real than we thought. Maybe it's more sophisticated. If you want more slow, intuition first science documentaries like this, subscribe. And here's a question to leave in the comments, because there isn't a single settled answer. And the best answers are usually the ones that take a minute to think through. If the universe is boundary first at the deepest level, what do you think is more fundamental, space or information?